Recording. Okay, hello and welcome to another wonderful adventure of the New York City Category Theory Seminar. David Jaz Myers is going to talk about contextads, the Kleisli and para constructions as a wreath product. Anyways, David, take it away.
Thank you, Noson. This is really nice to be here virtually. So I'm going to talk about contextads, which are this generalization of a comonad and a monoidal action, and even some other things that Matteo and I have been working on for a while. We came to this out of the para construction. And it just turned out that if you run this construction in a certain way, which I'm going to show you, it is more naturally expressed in a greater generality, namely the generality that turns out to be wreath products. So I'll explain what these are later. And once you have that generality, it's also clear that it works not just for what the para construction works for, but in other cases. And those other cases include Kleisli categories for comonads, as well as the span construction. So we're going to see all three of these as an example. So we decided to pick a general name, and that name is contextad. So that explains this weird name. But the idea is that we're going to try to axiomatize this situation that's quite common, where you have maps in a category that have some extra context floating around. So we're going to take this double categorical point of view. So suppose you have this blue category of ordinary non-contextualized maps. We're going to talk about what happens when you have another category going on with this extra context floating around. So here's three examples of this. One is if you take spans, you can think of a span category here.
Well, I'm sorry, David. Could you back up? What is a contextualized map?
A contextualized map is just a map where you have some extra context floating around. So let me go out of order and start at the really bottom one. So
Yeah.
suppose you have, say, some monoidal product on your category. Then you can take a contextualized map to be a map with an extra parameter space, P, right?
Yeah.
And then there's no reason ultimately to actually have the parameter space live in the same category as long as you have some monoidal action of a monoidal category on your category. And so in the other cases too, there's this sort of general story. It goes back to Kierberts in '99 that comonads are about contextual computation, where this is sort of the dual to Moji's work on monads in '91, where you think of a co-Kleisli map, or I'll just call it a Kleisli map from here on out of a comonad. It's a map from A to C. If you look at that map P there in the middle, it's a map from A to C, but it depends on some extra context that may be hanging around your element of A. So there's some fun examples of this. You can find online some fun Haskell tutorials of this, where you can see like the Gaussian blur of an image. It computes a pixel from a pixel together with the context of the pixels around it. So it's a contextualized morphism. And for span, we can also see that, imagine you have this sort of bundle of extra contextual data that you have over the domain A called P, and then we can map out of that. So we can map out of the whole bundle. So if you think of P as having a pair of an element in A and then some special element whose type might depend on the specific element of A, then this is a version of the last example, but that is dependently typed, if you will. So these are the three examples. We have these three double categories, classes of double categories: span, co-Kleisli, and para. And I'm going to construct them from the same bit of data. So just to keep going here, actually, let me talk about how we actually compose in these double categories. So in these double categories of contextual maps, we compose contextualized maps by combining context. So I'll start again at the bottom of the page. Actually, I probably should have reordered these. But at the bottom, what you can see is if we have a contextualized map P or P1 and a contextualized map Q1, right, then we can make their combination by putting together their parameter spaces, right? And then we just associate, and then we can use the first one with its context, and then after we get rid of it, we can use the second one. And then if we look at the co-Kleisli morphism, we have co-Kleisli composition there, Kleisli composition, right? And you can see it's actually have a very similar form. We take our C and then we duplicate the context, or we distribute the context. That's what the delta is, the co-multiplication of the comonad. And then we apply the first map under the comonad, and then we apply the second map. And the case of spans is similar. What we do is we take this pullback. And if you think fiber-wise, what taking a pullback is, it's taking a dependent sum. So we're combining the context we have here, and then we end up with this combined map. And as you can see in all three of these cases, we have this combination of contexts, and then we affect the first map by the context of the second map, and then we compose with the second map. So that happens in all three of these cases.
So just go back to the comonad. In the bottom thing with para, you have P1 is a comonad on the things that you're acting on, and Q1 is a comonad. So this is
no, way less complicated than this. Think of the tensor. If forget about the tensor and the dot for a second, that's an extra generality. Just think of it as being Cartesian product all the way through. P1 is a map from P1 times A1 to B1. And Q1 is a map from Q1 times B1 to C1. And we want to compose these. So so in other words, P1's a map from A to B, but we have this extra parameter in P. And Q1 is a map from B1 to C1, but we have this extra parameter from Q1. And so what we want to do is compose these, but we have to keep track of both parameters when we do it, right? So we that's what we have here. We now have this composite map whose parameters are from Q and P, right? Both the parameter spaces are together, and then we can feed forward the parameters and apply both of our parameter maps in turn. And similarly, the co-Kleisli example, these are just co-Kleisli morphisms. So Q1 gives you the general shape of a co-Kleisli morphism. It's a map out of something under a comonad. So there's a fixed comonad in this example.
C is the comonad.
C is the fixed comonad in this example, yeah.
Well, in the middle example, why don't you have a C and a C prime? In other words, you're just running it with itself.
This is just an example of a comonad. So C is a comonad. So it comes with this natural transformation delta, right? Mm-hmm. From C to CC, right?
Right. Okay.
And so we just use that. This is the ordinary co-Kleisli composition for a comonad. It's exactly dual. If you flip the arrows around, you get the Kleisli composition for a monad. If that helps.
Yeah.
But you might be getting it. There is a generalization here, which is we could mix and match. So instead of having this action that would give us para and this co-Kleisli, well, I'll go to the next slide. We could get this more general thing. But I'll tell you what our general thing is. We're going to unify the three constructions here into one single construction, which we call the context construction. And it's going to take in something we call a contextad, and it's going to give us a double category. This can generalize two things. It could generalize para. One way to see it is it generalizes para. Where para takes in an action of a monoidal category on a category and gives you this parameterized double category, we will take in a fibered colax action. Okay? And then it also generalizes co-Kleisli, where co-Kleisli takes in a comonad usually. We're going to supply it with what we could call a dependently graded comonad. So both dependently graded comonad and fibered colax action are just other names for contextad. And because we had these two different intuitions, we wanted to come to this general name that didn't bias us towards one or another intuition while we were writing. So
Dave, I have a question.
Yeah.
This doesn't have anything to do with like context categories of type theories, does it?
So that is an example of, if I go back up, right, in the span case, if we had a context category, we would have this class of display maps and they would appear on the left. So in that sense, you can think of that like that shows up there, but not in the same way. No, it does not have to do with the category of contexts of a type theory. It's more like we are adding extra context to morphisms.
Gotcha. Thank you.
And then the main new thing, also, I guess I've given I give a version of this. I give two versions of this talk last year while we were in development, and the project has developed for a bit. It's finally on the archive, which is wonderful. But the upside of doing this is that we're going to do it with this beautiful abstract nonsense, which is we're going to see that what this actually turns out to be is quote unquote just the wreath product of pseudo-monads and span cat. So a double category is a pseudo-monad in spans of categories. So just it's a categorification of the idea that a category is itself a monad in spans of sets. And there's this notion of wreath product, which I'll come to later, for monads. And it turns out if you just apply that in span cat, you get this thing, which I think is really quite cool. And because it's so abstract, we can actually do it in span of K for other two categories. And this, we will abuse this generality to be able to add structure to our CTX constructions or para constructions or co-Kleisli constructions. So we'll be able to find two algebraic structure on them. And this will generalize, for example, the sort of classic result that a comonad, which is colax monoidal, has a monoidal co-Kleisli category, which is probably more familiar in its dual form, that a lax monoidal monad has a monoidal Kleisli category. And we do get the dual constructions, of course, by just using duality, right? So I chose comonads here because I have more examples of these, and this is also what we were interested in. We were interested in para rather than copara. Okay, so let's talk about double categories of pseudomonads in span cat. So, right? So the idea is that the vertical category here is this category in blue on the right, if you say at the feet. And the horizontal categories is really not a category, it's really a horizontal bicategory, is appearing as this span. It's spanned over. So the objects at that top are the horizontals. The morphisms are the squares. And the fact that this is a span tells you that each horizontal has a source object and a target object, and each square has a source map and a target map. Okay? So the thing to notice about all of the categories of squares on the left-hand side is that they can be formed by pullbacks of spans of categories as on the right. And so this is just like a reformulation of what they are. So spans up top, well, a span is a pair of arrows with a common domain, right? So I can define the category of spans going vertically, right? Not horizontally, that's a different thing, but going vertically in the diagram on the left, as this pullback of categories, right? Of the two arrow categories and the two domain maps, domain projections. For the co-Kleisli category, similarly, a co-Kleisli morphism is a map whose domain is in the image of the comonad. So that's this pullback as presented in the middle. And for the para construction, again, we get a map whose domain is in the image of this action, the monoidal action. And so in all these cases, we get this composite of spans. And the right-hand thing in all these cases is is constant. It is a span in categories which underlies the double category of commuting squares in A. And those commuting squares in A show up on the left-hand side as those blue squares. You know, ignore the green stuff for a minute. The blue squares, essentially, that commute. Those are the commuting squares in A. And that's a double category. And we're composing something which maybe is almost like a double category with this. So it suggests maybe we're looking for a distributable. But it turns out that the thing on the left is not a double category. Well, it is for span, but it isn't in general in the other two cases. So in span, the thing that will yield span, it is a double category, and it goes by composition, and so its identities are here. I mean, I won't talk about it as a double category, but you have this identity, right, which is a trivial context, and then you have this composition, which is a sort of combination of contexts. Similarly, for Kleisli, what we have is a diagram like on the middle. We have this identity, but now it doesn't commute on the right. We have this two cell epsilon, which is the co-unit of the comonad, and we also have a multiplication. And here again, nothing really happens on the apex of these spans for a comonad, but you also have this two cell delta, and as you can see, it's a weird way to write a two cell that goes from C to CC, but it does go in that picture from C to C composed with C. Okay? And then finally, in the para case, we have this action, and we can write the data of this action in similar form. So you can see on the left, we have to pick up the monoidal unit, and then we use the co-unit there is the uniter of the action, and it's an isomorphism, but nothing actually requires us in this whole story to assume that this will be an isomorphism. If you don't, you get a colax action, which is sometimes also known as a graded comonad, graded by the monoidal category C. And in the right-hand side, we have the tensor of our parameter spaces, and then we have this delta, which is the associator, or the co-associator, if you will. Okay. So in all these cases, we almost get something which is like a monad, but it doesn't actually. It's not going to be a pseudo-monad in span cat. It's going to be a pseudo-monad in something else called F span arrow, which I'll come to in a bit.
Wait, David, I'm sorry.
Yeah.
You said co-Kleisli and para don't form double categories from the slide before.
I'm sorry. So what I mean, all these things on the left-hand side are double categories, right? That's the composite red span, right? But if I zoom in here, this is not a double category. This span a C, right? Its structure is almost like a monad structure in span, right? You have your unit and you have your multiplication, but they don't actually commute on both sides. They're not maps of spans. They have this extra two cell. And so they are pseudo-monads in some tri-category of spans, but just not span cat. And we'll come to what exactly it is later.
Gotcha. Thank you.
Okay. So there is an important thing to note about this that makes them special. In every case, the left leg of these things is a fibration, right? So if I go back here, the right-hand side is colax commuting. This is what I'll call a colax morphism of spans. And the left-hand side is going to be Cartesian for the left projection here, which is always a fibration. Okay? So David, do
you have a cursor?
Maybe. How is this?
Okay, so
yeah, I can do that. Is that all right?
So just go back and say what you just said 2 minutes ago.
Yes. Okay. So this kind of thing I'll call a colaxity. This kind of morphism of spans, like this or like this, I'll call a colax morphism of spans. But the extra thing to note is that all of these things here, and in this case, this one and this one and this one, right? These are all fibrations, right? They're all fibrations. In this case, codomain is a fibration because in order to construct the span, double category, we need to assume A has pullbacks. And this map in the middle here is going to be Cartesian for that fibration. And in this case, like the product projection is a fibration because you can just re-index. You don't have to mess with the second component. This is an identity. So its Cartesian lifts are given by, the identity. And this one is the codomain fibrations given by pullback. And so, so that's the setting we're in to note that this is a special setting, which I'm calling F span arrow. So what do we do with that fibration? Right? Well, it actually appeared in our composition picture as this purple stuff on the left here. So remember when we compose spans, right? we have to take our P here and we have to multiply it. We have to pull it back along this Q, right? Or in other words, if we have our P here, we have to apply the comonad to it before doing the Kleisli composition, right? And another thing is here, if we take our P here, we have to act on it with the context of the second thing we're gonna do. And each of these cases, when we write it out in cat, as it looks like in cat, which is what's happening on the right, it's given by the structure. It's induced by the structure of the Cartesian fibration. So the codomain fibration here, pull here is the pullback. So it's the pullback of the fibration. So you take a map in the base that is landing in the projection of the target of the total space, and then you pull it back to a new element. And this one here is the Cartesian lift. So that's the pullback together with its universal comparison, its universal Cartesian lift. And putting these together induces this lambda here, which, if you'll note, this lambda swaps. In either case, it swaps the top of the it swaps the order of the composition of these spans. So it's very much starting to look like lambda would be a distributive law, right? But remember that the thing would be a distributive law between half of those things aren't double categories, right? It looks like we're having a distributive law between double categories, but these things here, they're not double categories, right?
Sorry, David. The only thing I've ever heard of is a distributive law of monads. Can you remind me, so you're saying because there are pseudo-monads in
yes,
span
a double category is a pseudo-monad, and if you and so and this is a double category. It's a pseudo-monad. If this was a double category, right? In fact, in the span case, it is, right? Then we're asking how to put a composite on their how to put a monad structure on their composite, and that is what distributive laws are usually for.
I see. So you're saying if that thing on the left was a pseudo-monad, this would look like a distributive law between the two pseudo-monads.
Exactly.
Gotcha.
Exactly.
Cool.
And so what we're going to see is it's not a distributive law, but it's the other kind of thing that appears in the formal theory of monads known as a wreath product. Okay, so now I'm gonna do some. Now we're gonna see the general setting for this and how this works. Okay? So I'm gonna define this thing called a paradise. You can always think of this as being cat for now, although at the end of the talk I'm going to swap it out for other two categories. And so for now we can just imagine it's cat, but right. And then given in cat, we can describe between any two, let's say categories, A1 and A2, which appear here, we can describe this two category. So its objects are spans, right? Its morphisms are these kinds of things, excuse me, right? The colax morphisms of spans. So they commute strictly on the left and colaxly on the right. And the two cell is a two cell like alpha, which makes this commute. Right. So these are two categories between any two categories, any two space categories. But they don't assemble into a triple category. And the reason is because when you try to compose spans by pullback, well, you have this colaxity here. You can no longer use the universal property of the pullback to induce a map on the composite. So we will get tri-categories, namely spans, span K, which is the special case where gamma is the identity, right? These gammas are the identity. That's the ordinary span morphisms. And then you get a tri-category where you're taking actual pullbacks of categories. So it's strict pullbacks, by the way, here everywhere. And then there's another case in which we compose these. If these things on the left are fibrations and the C maps are Cartesian, then we can organize that into a tri-category as well. And the way we do that is we use, if you imagine us having, I'll just write it here, imagine us having another span here, right? And we're trying to form the composite, right? We're trying to form this composite here. Well, what we can do when we want to map in here is we can lift the orange two cell, which would be here. Sorry, we can lift this two cell. Use this two cell along this fibration, and when we do, we get it out of the way, and then we can use the universal property of the pullback.
What is a fibration in an arbitrary two category?
That's a good question. A fibration in an arbitrary two category is I'll come to a definition in a bit. Maybe I'll just say it, but it can be expressed as a sort of algebra for this monad of slicing, essentially. So it's essentially the well, I'll go back up here. You see, this structure here is the pullback functor, and that, as you can see, is we're taking this thing here, which is a double category, and we're acting it on here, on these things here, right? So this is a double category. It's a pseudo-monad in span. We're acting on it on the left here, right? And we're taking an algebra for the resulting thing.
Oh.
And that is what a fibration is, as it turns out.
Oh, okay. Interesting.
And so this goes back to street. That my quote at the very beginning, you are about to witness the strength of street knowledge, is because we just end up using so many ideas due to street in this work. Street and also Steve Black as well.
Yes.
Okay, so I'm not going to describe this in great detail. Well, that's not true. I'm going to go ahead and describe it a bit. But so let me talk about what a contextad is. I'll finally give you a definition. So a category internal to K, which I'm just going to call a double category. Remember that we're pretending that K is cat, is a pseudo-monad in the spans, right? We're the strict composition. But a contextad is a pseudo-monad in F span arrow, right? And so they have the structure map here, which I hope is familiar from a few slides back. But note that here, this thing is a fibration. So this is why we thought we also called them fibered colax action, because you have a fibered action, which is colax. But we could also call them a dependently graded comonad, because you have a category of grades, which depends on A, which has a comonad structure epsilon delta. There's I don't have time to talk about it in this talk, but it's actually a very nice story. Dependent to view these things as dependently graded comonads, you get a very nice story where you can see that many monads that we think of as side effect monads actually have transposed into dependently graded comonads with equivalent Kleisli categories. So that the context construction of the contextad is equivalent to the Kleisli construction of the monad for any polynomial monad. And so that's a nice whole nother story, but you can check that out in the paper if you want. It's sort of it's not fully done out in the paper, it's sketched, but the idea of looking at them is if you're into Kleisli categories and comonads for contextual computation, that there's a nice story to be told there where you can use dependent types. Okay, so here are two important lemmas. We're just going to rearrange things. So if I have a diagram like this, right? Note that I can take this pullback here. What is this pullback? This is the slice category. So I take the arrow mapping down into here from B arrow. I take like B arrow mapping down into here, right? And I pull back. That gives me the slice. By the universal property of the slice, I can take these and turn them into single maps into the slice. Right? And I can take this, two cell and put it with it too. So in other words, what you can see is that the two category of colax morphisms between spans, right colax morphisms between spans, is equivalently to the Kleisli category for on strictly commuting spans, which these are strictly commuting, right? For the action of B arrow on the right. Okay? And then what I said above, sorry, yep.
Sorry, I'm just trying to parse this here. So what's the difference between D-span and F-span again?
D-span is sorry, I should have said this before. D-span is just that these maps here on the left are assumed to be display maps, which just means we can pull them back. So in cat, it's anything. In cat, there's nothing different. F-span means F-span will always be F-span arrow. This is D-span arrow. It's not a tri-category, but it's just a halfway stop on our lemma, basically. But F-span looks like D-span, except these are actually fibrations.
And F-span is a tri-category?
F-span is a tri-category because when these are fibrations, you can compose by pullback by sort of lifting these out of the way using the Cartesian lift.
Okay. So then D-span A, B should be a category, though. D-span is a two category.
D-span arrow AB is a two category, but it doesn't compose in A and B. Right?
I see.
And
okay.
D-span is a tri-category, right?
I see. Okay.
But D-span AB is the two category of we're fixing A and B here. So.
Okay.
And then, so the second lemma, and this is sort of a generalization of what Street does in this paper on fibrations by categories, is that the just having D-span, but the property that this thing here is a fibration, and the property that these maps here are Cartesian, means you're working in the category of algebras in this two category for the monad on it given by composition on the left by the arrow monad, the arrow pseudo-monad, which was the double category, right? And the way it works is that you have your pullback is the algebra structure, as you can see, but it actually, there's some other thing that goes with the pullback, which is the canonical lift. And so you need to put that somewhere. And so you put it in the right. And so you can put these two lemmas together. And what you get is this equation, right? And that equation is very suspicious, this side in particular. Algebras by an action on the left of the Kleisli category of an action on the right in something, right? That formula there is the formula that Lack and Street give in their paper, Formal Theory of Monads 2, for the free co-completion under Kleisli objects of monads, but they do monads. We're doing pseudo-monads, so we need to bump up a category level. Where we used Adrian Miranda's thesis. He did a lot of work in his thesis, and in particular, he constructs this tri-category, which was really a blessing for us. He found a problem with an earlier version of this project where we were being a little too strict, and you really do have to go tri-categories here, unfortunately. But luckily for us, he had worked that out. And so when I say free co-completion under Kleisli objects, it's not very, I think, as well known as it could be, but Kleisli categories are a certain two-categorical colimit of the monad itself. So you think of the monad as sort of a diagram, a two-categorical diagram, and you take its colimit of in a certain way, you get the Kleisli object. So we can freely co-complete under them, and then by using Yoneda, you can sort of just compute out. It's slightly more involved in this. But the essential argument is you just compute out that its Homs must be of this form, algebra for the action on the left into Kleisli of the action on the right. And that sort of just uses the universal property of Kleisli's. The limit of the monad is the category of Eilenberg, the Eilenberg-Moore category of algebra. So there's a really precise sense in which the Kleisli category is the dual of the Eilenberg-Moore category. It's a really cool point of view. And so what we found here is that F-span arrow is in fact a fully faithful sub-tri category of the Kleisli co-completion of spans. And so in particular, it's the full sub-tri category spanned by the arrow monads. Okay. So now what we can do is this really fun thing where because KL is a free co-completion, right? It has Kleisli objects. And because KL is a free co-completion, I should circle this one, because KL is a free co-completion, we can extend any functor into something with Kleisli objects uniquely up here to the Kleisli of it. So we extend the identity and we get this sort of monadic composition of Kleisli, and that's called the wreath product. And this is going back to Lakenstreet again. And so now, if we just run out what the wreath product says to do from Lakenstreet, we find that it actually produces the CTX construction. And this includes the span, Kleisli, and para constructions, right? And so this is just this long formula here. That is the wreath product formula. So you use lambda, which swaps these two. Then you compose on here. Then you use this structure, which is the tensor and delta, and that actually picks you up from, you take these two and you go into these two. So you add as you can see, it's almost like this C here, almost like a monad. If it just landed in C, it would be like a monad. But it's not. C, the multiplication lands in this composite here. And then we have we have two of these and we compose them. And if you run through all the examples earlier in the slides, you'll see that this is precisely what all of them are saying. So I'll do that really quick. Way back here, right? See, what we have is we take what we're doing is we take our first thing, we swap it over using the context of the second thing. We combine our contexts, and then we compose the resulting morphisms. So here, we take our first thing, we swap it over the context of the second thing by putting it under C. We combine the context by precomposing with delta, and then we compose the result at the end. And similarly over here, we take our first thing, we swap the context with the second thing, we combine contexts, and then we compose the result. And that's what this says.
David, can you
swap the context over, precompose, and then combine the context. Yeah.
Can you give an example of wreath product for just normal monads?
So all distributive laws are wreath products. There's another fun thing, and this has implications for here, which is that wreath, if you think of categories as monads in span set, then wreath products include the orthogonal factorization systems, which is kind of cool. Whereas a distributive law is a strict factorization system. A wreath product allows for the looseness you need for just orthogonal factorization systems.
So the classical version of this result that you're talking about, it would be span of sets, and I take KL of that.
Mm-hmm.
Okay.
There's not, yeah. So that they Lakenstreet consider that case, and they show that you can compute KL of span set in a nice way in terms of it's the Kleisli 2 category of the free coproduct completion construction comonad. The free coproduct completion monad on cat, as it turns out. It's equivalent to that. And the same thing should be true for double categories, by the way, in the double categorical in span cat setting. But we haven't done that. Like morally, that should be true as well. It should be the free vertical co-completion comonad Kleisli category. And that has actually, there is an important thing about that, which that's how you end up getting these relationships to polynomial monads or parametric right adjoint monads, because those are right adjoints in FAM, in KL FAM. Okay, but enough of that. Okay, so now I want to show you so this was very general. As you see, there's nothing that required us to be working in for K to be cat here, right? So we can just take it to be other things, and that's what we're going to do here. So two algebraic structure. By two algebraic structure, I mean algebraic structure on a category. So what you can think is, for example, symmetric monoidal structure. It's governed by, just as algebraic structure is governed by monads, two algebraic structure is governed by two monads. And so we will consider the two category of strict algebras. So they're just so a two monad is a strict like it's a monad just in the two category, right? So it has to commute with the it has to be a two functor, but all the structure is strict. It's like one categorical. So we can take strict algebras for it. Those are just algebras for the monad in an ordinary sense. But now, because we are actually in a two category, when we go to write down the homomorphism square for an algebra of a monad, we can actually stick this two cell in here. And that's a colax algebra. So for example, if T was symmetric monoidal category two monad, then this would be a colax monoidal functor in the usual sense. If you flip the arrows around, of course, you get a lax one. Right? So now we can say what it means to be colaxly T-structured for a double category, and what this is going to be in the case of symmetric monoidal, if for T equals symmetric monoidal category monad, it will be a lax monoidal double category. So what a colaxly T-structured double category is, it's a pseudo-monad in D-span, right? For which both of the structure things are T algebras, right? So D naught, D1 are T algebras. T and T, S and T are strict T morphisms. So that's the same thing as a colax T morphism, but the colaxity is an identity. This equals, right? But all the other structure, so that's the composition, the unit, the composition, and all the coherences, they're all colax morphisms for T. Okay? So if you take T equals SMC, this gives you lax monoidal double categories. The reason that you switch from having this colax to lax is because while it's true that all this stuff is colax morphisms, you can also see it as a monoidal object in double categories with lax functors. I'll note that if this is a isomorphism, you call this a pseudomorphism, and then you can do this again for pseudo T-structured things. And if you do a pseudo one, you will actually get what's called a monoidal double category. So the reason we're doing this is because we want to get monoidal double categories out, right? Spans a monoidal double category. If your comonad is colax, you will get a colax monoidal, you'll get a monoidal double category. And in the case we originally started with, is if your if your action is symmetric monoidal or like is symmetric monoidal, if you take a symmetric monoidal category acting on itself, you take its paraconstruction, that is a symmetric monoidal double category. So the way we do this is we're just going to run our construction in algebras with colax morphisms. And this requires us to actually be able to take pullbacks in that, which turns out to be a technical result. And it again relies on a lot of ideas of lax. So in this case, work from Lackenberg on rectifying isocommas into strict pullbacks. We use a similar method to rectify a comma into a strict pullback. So if we have a contextad in K, so that both A and C are T algebras, and pi here is a strict T fibration, right? And as a technical result, it has to be normal as a fibration, which means Cartesian lifts of identities have to be identities, which is a very minor condition. And all the structure is colax, right? Then our theorem is that the context construction of this is a colaxly T-structured double category. And so the proof of the theorem says, basically, just run the colax construction in alg TC. And then you don't quite get everything for free there. You have to just check that the target is strict. And that turns out to follow. So the lemma here is important. This is why we need to add this display map thing, because not all pullbacks exist in this category, in this two category, but the ones that are strict display normal fibrations, which is what we assumed our pi was here, they do pull back. Okay. So you can actually run the whole construction there. And so this has a number of corollaries. It's all the ones I said. So, one of the things, so if A and C have some limits and pi preserves them, right? then CTX is a double category, and it's going to have those limits in the type direction or in the vertical direction laxly. If the action itself dot also preserves them, then it's going to have these limits double theoretically. So if all the other structure also preserves them, so it's not just the action, but also the tensor and the one, that's the preserved limits. Then all of this, then the resulting double category will have it double theoretically. This occurs in the span case. So it lets you construct the double limits in span like this. So a colax monoidal comonad, right? What is that meaning? Well, remember, in that case, this was the identity, and this was the comonad. Well, we asked that these are all colax T morphisms, right? So in particular, this is colax. So in the comonad case, you're having a colax monoidal comonad, and you get a monoidal Kleisli double category at the end. And then the really general form of the action is not the symmetric monoidal thing I said, but in fact, if you have a duoidal action of a duoidal category, and a duoidal category is a monoidal category internal to a pseudo-monoid internal to monoidal categories and colax morphisms, then you get a lax monoidal para double category. And if you add pseudoness to this, if you add pseudo to that, you don't get duoidal, you get braided. And then you get with just braiding, you get a monoidal double category. And if you have symmetric, you get a symmetric monoidal double category. So, yep. That's the whole thing.
Well, thank you very much.
Thank you.
One second. Let's. So David. One second. So don't. Let me put everybody on now. Thank you. Everyone's clapping. Any questions?
Yes, if I may.
Yeah.
Please.
So you get these different contextads, right? That you introduced in the beginning as examples. Are there any like natural morphisms between them?
Yeah, great question. So this is actually, the context construction is actually a trifunctor. And the morphisms are the morphisms you want in all these special cases. So the morphisms, well, there's sort of, you could use the whole morphisms coming from KL, but that's usually too much. Those are, I mean, sometimes they can be interesting. I think Matteo knows more cases than I do about that. But in general, you want to restrict them to where the span is actually a functor, like as in his left leg is an identity, and then you get something that is in the action case, you get morphisms of action. So you get monoidal, pseudo-monoidal functors of the acting categories, and then this colax morphism of the actions, and that induces by the functoriality of this, that induces a functor on the parakin categories. Similarly, for comonads, you get the usual intertwining morphisms between comonads. So the definition that is also due to Street of intertwining morphism between comonad, I think it's due to Street, in the formal theory of monads. You get that out as a morphism between the comonads, and of course that induces a morphism on the Kleisli double categories. And in the span case, I think you can push forward a finite product preserving thing into one of those morphisms and get the resulting functoriality of span in finite limit preserving functors. So yeah, they do show up. Yeah.
Cool. Yeah, actually, this went in a slightly different direction than I intended. But no, I was actually thinking. So you get these tri-categories, right?
Yeah.
I mean, are there any natural morphisms between those tri-category examples? Functors.
Between the trifunctors? Which trifunctors?
So you. Okay. So
there's only really one trifunctor we construct, which is this big one.
Right. Okay. So maybe I should retract this and think about it more.
So the reason we did this originally was Matteo essentially nerd sniped me about this really cool triple category he was playing around with for use in controlled systems, controlled dynamical systems, or cybernetics, categorical cybernetics, and it was sort of evidently a para construction that was applied to a double category and yielded a triple category. And so, in the course of trying to figure out how to do such a thing, we ended up with this. So we actually can use this. The whole reason we did this is so we can construct a symmetric monoidal triple category, which of course is a horrifying thing if you imagine trying to do that by hand. But this produces it. So.
All right. Yeah. Thanks.
Are there any other questions? Anybody else? Okay, well, let's thank the speaker again. David, thank you very much.
Thank you very much.
Yeah. Next week at the regular time, in-person talk, Emilio speaking. Emilio, you're speaking about sheaves. Hold on, let me... Emilio, tell us what you're talking about.
This decision problem as
sheaves, yeah. Right. Anyway, so we'll see you all next week. Hopefully, if you're in town, you're welcome to come. David, thank you very much again.
Thank you very much.
Anyways, and thank you everyone for coming. Thank you. Take care.
Thank you. Bye-bye.
Bye-bye.